Your fingers knew the needle valve before your mind did. This is the thing about engine tuning that people who have never done it find almost impossible to understand from the outside. It was not a procedure you read from a manual and executed mechanically. It was a conversation, the needle valve of a Veco, a small, precisely machined brass, fitting threaded into the carburetor body at the end of a shaft no wider than a finish nail, communicated through your fingertips with a sensitivity that exceeded what you could see or measure. A quarter turned clockwise, and the engine leaned out, the note climbing from the rich burble that was comfortable but slow into something harder, more urgent, more purposeful, and too far, and it crossed into the lean run, that high, tight, urgent sound that carried warning in it, the sound of insufficient lubrication, running the engine toward a temperature it was not designed to sustain. And a quarter turned back, and the power band settled. The propeller note took on the specific authority of an engine running correctly, and the circle tightened. The fuel had a smell that was total and immediate. Methanol and castor oil, and whatever percentage of nitromethane the pilot was running, the castor oil, warm and faintly organic, the methanol sharp and clean in the sinuses, the nitromethane adding a heat that you could feel before you smelled it if you leaned too close. The Veco fuel tank was a small tin or aluminum cylinder mounted ahead of the firewall, the brass tube extending into the fuel, the feed line running back to the carburetor with the specific care that the plumbing of a running engine required. Not too long, not kinked, properly sealed at both ends with the patience that any fuel system rewarded with consistent delivery and punished without mercy when it was inattentive. You flip the prop with your finger, the index finger along the blade, away from the arc, which was the technique and was not optional, because the alternative was the technique of people who had not yet learned why the index finger was along the blade. The Veco turned over with the specific compression of a well-fitted engine. Tight, authoritative, requiring the specific flip that committed to the stroke rather than the half-committed glance that produced nothing. The glow plug's coil, heated by the battery clipped to its terminal, was orange at the correct temperature. The fuel hit the chamber and the engine fired. And then you were standing at the center of the circle, with the handle in both hands, the lines going out to the model at the end of them, and the sound of the Veco at full song filling the sky around you. Not a gentle sound, not a polite sound, but the raw two-stroke certainty of a small engine turning an 11x5 propeller at 11,000 RPM in the open air, a sound that announced itself as something real, something that had been made to run and was running, something that required and rewarded the attention of the person at the center of the circle. The question this story asks, and it is a question that the story cannot fully answer, because the answer involves things that happened in the culture as well as in the market, is this. Did Veco disappear because technology moved on, or because we stopped valuing the kind of precision that required patience to understand? If you remember the smell of castor oil on your hands at the end of a flying session, that organic, faintly sweet residue that stayed on your fingers long after the fuel had dried, that showed up on anything you touched for the rest of the afternoon, take a moment to like this video and subscribe. Not for the algorithm, but so stories like this one don't fade away. The culture of glow engine, tuning, and control line flying, and the specific knowledge that these activities produced in the people who practice them is worth keeping in the record, and keeping it there requires people who carry it to say so. Gil Henry founded what would become Veco Products in the late 1940s, when it was still known as the Henry Engineering Company, operating out of California in the specific context of the post-war West Coast precision manufacturing scene. Henry was a machinist with the kind of relationship to metal that develops when you spend years working with actual cutting tools on actual material, not the theoretical relationship of the engineer who designs but does not cut, but the practical, felt embodied knowledge of someone who has learned what metal does under the tool and can hear and feel when the relationship between the tool and the workpiece is correct. The first Veco engines reflected this background. The 3-bolt backplate models that the Henry Engineering Company produced in the earliest period were engines that showed their origins in the hands of a machinist who understood fit and finish not as aesthetic goals, but as functional requirements. The tolerances were tight. The fit between piston and sleeve was close enough that new Veco engines typically required a careful lapping-in process before conventional break-in, the modeler working the parts against each other with a fine abrasive compound to ensure the contact surfaces were perfectly mated before the engine was asked to work under load. This was not a flaw. It was a philosophy. The engine that was fit correctly to begin with would wear correctly over time and maintain its precision longer than the engine that started with looser tolerances and depended on running in to achieve what machining should have produced. The Series 100 redesign replaced the 3-bolt backplate with a 4-bolt configuration that improved structural rigidity and made assembly and disassembly more straightforward, without sacrificing the dimensional accuracy that the original design had established. The engine sizes that Veco produced covered the range of the typical hobbyist's applications. Which was a natural size for control line trainers and sport models in the 12 to 16 ounce weight class. B, which moved up into the larger sport models and the beginning of the competitive stunt and speed classes. D, and which covered the serious competition applications where power to weight ratio and consistent output mattered as much as peak horsepower, and which was the work of Clarence Lee, and which would prove to be the most enduring product the Veco name produced. Clarence Lee's was designed while Lee was working in the sphere of K&B Manufacturing, and the design found its first production home under the Veco name, before the engine line was absorbed into K&B's catalog after Veco closed. That they continued in essentially its original form for approximately 27 years after Lee designed it, outlasting Veco itself by decades, continuing to be manufactured and sold by K&B as one of their flagship engines, is a specific kind of testament to the quality of the original engineering. And a design that sustains production for 27 years is not a design that was correct by accident. It is a design whose fundamental proportions and manufacturing specifications were right in the way that fundamental things are right, not because they were optimal for a specific narrow application, but because they were right across a range of applications and conditions that the designer did not fully anticipate. The reputation that Veco engines carried in the control line and early radio control communities was organized around a consistent set of reported qualities. They were tight. The close tolerances that the machining produced made them feel different in the hand from engines whose fit was more approximate, and experienced modelers reported being able to feel the difference before the engine was even started, in the specific resistance of turning the propeller through the compression stroke by hand. They broke in hard. The lapping and careful initial running in that Veco recommended, and that the close-fitted engine required before it would accept sustained operation, was more demanding than the break-in that other manufacturers specified. But they rewarded the patience. An engine that had been correctly broken in and was properly maintained could run for years with the same power output and the same precision of tuning that it had produced when it was new. The world that received Veco engines was a specific American world of the 1950s and 1960s and into the 1970s, a world organized in the model aviation dimension of its life around the flying field and the hobby shop, and the informal community of people who shared a practice and a body of knowledge that was not available through any formal educational channel. Control line flying was at its peak in the 1950s and 1960s, the primary form of model aviation in the United States, not radio control, which was expensive and technically demanding in ways that limited it to a dedicated and relatively affluent minority, and not free flight, which offered no real-time control over the aircraft and required the specific patience of watching your model go where the thermal took it. Control line. The two thin steel lines connecting the model to the handle in the pilot's hand, allowing control of the elevator and through it, the model's altitude and behavior, was the form of model aviation that the mass of the American model flying community engaged with. Because it was accessible and because it was genuinely engaging, the pilot at the center of the circle was actively flying the model, making real-time control decisions, developing real flying skill in the specific context of a tethered relationship between hand and aircraft. The flying field for control line work was often the simplest possible, a patch of level ground, ideally paved or closely mowed, large enough to accommodate the radius of the flight circle plus a safety margin, parking lots, schoolyards after hours, the flat sections of parks that the city maintained for other purposes, but that the local flying club had negotiated access to on weekend mornings, cracked asphalt in the afternoon light. With the model at the end of the lines and the pilot at the center, and the specific sound of an engine at full song, filling the air around the circle in a way that the neighborhood understood meant something was happening, something small and fast and impressive. The competition classes that organized control line flying gave the culture its formal structure. The Navy carrier class, where scale model carrier aircraft were flown at specific airspeeds and landed on a simulated carrier deck, a raised platform at the edge of the circle, with their tail hooks catching a wire just as the full-scale aircraft caught the arresting wire on an actual carrier. The stunt class, where the model was flown through a prescribed maneuver sequence that included overhead eights, four-leaf clovers, and loops of specific geometry, judged for precision and smoothness and the specific aesthetic quality of a well-flown pattern. The speed class, where the only measurement was how fast the model could fly the required number of laps, and where the engine tuning was the primary variable. The needle set as lean as the engine would sustain, the fuel nitro content as high as the rules permitted, the prop as fine as the balance between speed and efficiency allowed. Each of these competition classes developed a specific body of technical knowledge around the engine and the aircraft and the combination of the two. Speed pilots understood air density and how to compensate for it with needle valve adjustment and stunt. Pilots understood the relationship between the engine's throttle response and the model's behavior in the vertical portions of the pattern. Navy carrier pilots understood the precise fuel delivery that the carrier landing demanded. The engine had to be set to maintain correct airspeed without the active management that the fixed throttle control line mode didn't allow. These were real technical problems, and the people who solved them were developing real technical capabilities that transferred beyond the flying circle into every other domain where problem solving under constraint was required. The hobby shop was where Veco engines and accessories first entered the hands of the people who would use them. The Veco product line extended beyond engines to fuel tanks, control horns, wheels, spinners, and the various small precision components that the model builder needed to complete and operate a flying aircraft. And the fuel tanks were a Veco specialty, precisely made small tanks in the sizes that various engine displacements required, with the correct tube dimensions and the correct clunk weight at the end of the fuel pickup tube that allowed the tank to feed the engine correctly through the full range of flight attitudes. A Veco fuel tank was not merely a container. It was an engineered component that had been designed by people who understood what a running engine needed from its fuel delivery system and had built the tank to provide it. The Veco Dakota was the kit side of the Veco product line, a model aircraft kit designed to work with Veco's engine accessories, giving the buyer a complete system rather than a collection of components that had to be made compatible through improvisation. The Veco streamlined sponge wheels, the Veco control horns, the Veco spinners, each of these was a component that had been designed with specific attention to the application it served, and the specific attention showed in the way the component performed compared to generic alternatives. And this was the completeness that a serious manufacturer provided, not just the headline product, but the ecosystem of supporting components that allowed the headline product to function as intended. The technical relationship between a control line pilot and a glow engine was an education in mechanical systems that had no equivalent in any other context available to American children and adults in the 1950s and 1960s. The automobile, which was the other large mechanical system that American culture interacted with regularly, was by the 1950s essentially opaque to the average owner. You drove it, you filled it with gasoline, and when it failed, you took it to a mechanic whose access to the system was not available to you. The glow engine was different. It was small enough to hold in your hand. Every component was visible. The relationship between the components was legible. When something was wrong, the engine told you in a language that was specific and interpretable, not through a warning light or a diagnostic code, but through the sound and feel and behavior of the machine itself. This interpretive skill, the ability to diagnose a glow engine's condition by listening to it and feeling it and reading its exhaust smoke, was the central competence of the serious model pilot, and Veco engines were among the best instruments for developing it. The closeness of their tolerances meant that the difference between correct and incorrect operation was more clearly expressed in their behavior than it was in engines with looser fits. And when a Veco was running correctly, it was clearly running correctly. The power band was smooth, the transition from idle to full throttle was crisp and linear. The exhaust note was the specific clean tone of a matched piston and sleeve at the right temperature. When it was not running correctly, the deviation from that baseline was equally clear. The hesitation in the mid-range, that meant a slightly lean main needle. The roughness at idle, that meant the idle needle needed attention. The heat that came through the cooling fins under your fingers that told you the glow plug was running hotter than it should. You carried the knowledge of your engine in your hands. This is a precise statement. The modeler who had tuned the same Veco through 100 flying sessions had developed, through those sessions, a physical memory of what the engine required. They knew without conscious recall how far to open the needle valve from the fully closed position to get within range of the correct setting for the fuel they were using. They knew the sound of the engine at the correct operating temperature. They knew the smell of the exhaust at the right mixture, the castor oil in the fuel burning at the right ratio, producing the specific odor that meant combustion was happening correctly rather than too lean or too rich. This knowledge lived in the hands and the ears, and it was not transferable through description. You could tell someone what the correct Veco needle valve setting was in abstract terms, 1 1/4 turns from closed, adjust from there, But that description was not the knowledge. The knowledge was the felt experience of 100 small adjustments and their consequences, assembled through practice into an intuition that was available instantly when the engine was in your hands rather than after deliberate consultation of remembered description. The glow plug was the component that most directly communicated the engine's condition to the pilot who knew how to read it. The Veco engines use standard glow plugs of the type common to the American model engine market, a specific heat range for a specific application, the idle bar plug for throttle applications, and the straight element plug for fixed throttle running. When you removed a glow plug after a run and examined the element under good light, the element's color and condition told you about the combustion that had been happening inside the engine. A tan or light gray color meant the mixture and the temperature had been correct. And a white or chalky element meant the engine had been running lean, consuming the element faster than it should. A dark or sooty element meant the mixture had been too rich, the combustion incomplete. The glow plug was a report card, and reading it was a skill that the experienced modeler had developed through the specific education of pulling plugs after runs and comparing what they saw with what the engine had sounded like during the run. The prop made its own contribution to the conversation. The propeller size, its diameter, and its pitch determined the load the engine ran against, and the engine's response to the load told you whether the combination of prop and fuel and needle setting was matched correctly to the application. An engine that was prop hung, that could not accelerate cleanly through the throttle range because the prop load was too great for the available power, sounded different from an engine that was correctly matched to its propeller. The experienced modeler heard this, adjusted the fuel mixture or the prop size or the needle setting, and found the combination that produced the clean linear power delivery that was the signature of a correctly set up glow engine. The lapping in that Veco recommended for new engines was a specific practice that communicated the company's values directly to the person who performed it. You mixed a small amount of fine abrasive with fuel, installed the piston and the sleeve together in the crankcase, and worked them through the range of their motion repeatedly, letting the abrasive carry away the microscopic high spots on both surfaces until the contact was uniform across the full stroke. And then you cleaned the abrasive out completely. Every trace, because the abrasive that remained in the engine would grind rather than polish, and began conventional break-in. This process took an afternoon. It communicated in the most direct possible way that this engine was worth the patience required to prepare it correctly, and that the patience would be rewarded by the performance and longevity that the correctly prepared engine provided. The Veco company closed in the late 1960s, and the disposition of its assets told the story of what the company had built and what others recognized as worth preserving. The kit line went to Dumas, which continued to produce model aircraft kits for the subsequent decade. The engine line went to K&B Manufacturing, where it was integrated into their catalog and where specific Veco designs, and especially the that Clarence Lee had designed, continued to be manufactured. The K&B that continued in production for decades after the Veco name disappeared from it was the Clarence Lee design in essentially its original form, perhaps the clearest possible tribute to the quality of the original engineering. The broader model engine market that Veco had participated in was through the late 1960s and into the 1970s undergoing a shift that would eventually leave the American precision engine manufacturers in a fundamentally different competitive position than the one they had occupied in the decade of their greatest influence. The Japanese manufacturers OS Engines, Enya, had been building quality model engines since the post-war period. And by the mid-1970s, they had developed to the point where their products matched or exceeded the American competition in the dimensions that serious hobbyists used to evaluate engines: smoothness, power, consistency, longevity, the quality of the machine surface. They also had the advantage of the manufacturing efficiency that Japanese industrial culture had developed, which allowed them to offer engines at prices that the American domestic manufacturers found increasingly difficult to match. This was not a failure of American engineering. The Veco engines, the K&B engines, the Fox engines that the American model aviation industry had produced were genuinely excellent machines, designed and built by people who cared about precision in the way that the best craftspeople always care about it. What changed was not the quality of the product, but the economics of its production. And the economics were driven by forces that had nothing to do with the quality of the engineering or the commitment of the engineers. When a comparable product could be made elsewhere at a substantially lower cost, the market responded to the price difference in the way markets respond to price differences, which is to say that it moved toward the lower cost product. The hobbyists who made this choice were not wrong. A serious pilot chose over a more expensive American alternative, flew their aircraft just as well, and required the same skill to tune and maintain. The skills that the glow engine demanded did not disappear simply because the engine came from Nagoya rather than from Los Angeles. And what was lost was something subtler: the specific, local American engineering culture that had built those engines and that had organized the hobby shop knowledge and the flying field culture around its product. The expertise that had accumulated in the American model engine industry, in the machinists who had run the lathes, in the counter people who had known the products, in the competition pilots who had developed the tuning techniques, dispersed when the manufacturing dispersed, and it did not reconstitute itself around imported products in quite the same form. The control line flying that Veco engines had primarily served was itself losing ground through the 1970s and into the 1980s. Radio control technology, which had been expensive and technically demanding in the 1950s and 1960s, improved steadily through the 1970s in ways that made it genuinely accessible to a much broader population. The synthesized crystal frequency systems replaced the older tunable units. The servo response times improved. The reliability of the radio link improved to the point where the risk of a loss of control, which had been a serious concern for control line pilots considering the transition to RC, became manageable. And by the early 1980s, radio control had displaced control line as the dominant form of powered model aviation. In the specific culture of the control line field, the pilot at the center of the circle, the specific skill of managing the elevator through the lines, the community of pilots who flew their aircraft in the same shared circle had become a minority practice within the broader hobby. The control line pilot who transitioned to radio control found that many of the skills transferred: the engine tuning, the mechanical preparation of the aircraft, the understanding of what the model was doing in the air, and why. What did not transfer was the specific intimacy of the connection between the pilot and the aircraft that the lines had provided. The control line pilot felt the aircraft through the lines, felt the lift as the model climbed into the inside of a loop, felt the load on the outside wing when the circle was too tight, felt the model's preference for one direction of turn over another, which told them something about the trim that needed adjustment before the next flight. The radio control transmitter was a different kind of interface, more capable, more versatile, and more distant in the specific sense that the feedback was visual rather than tactile. You saw what the aircraft was doing. You did not feel it. The almost ready-to-fly revolution that arrived in the late 1980s and accelerated through the 1990s changed the experience of the RC hobby in ways that were commercially successful and culturally significant. The era of aircraft arrived from the factory largely assembled, requiring only the installation of radio and engine equipment and a few hours of preparation before it was ready to fly. This removed the building process, the construction of the aircraft, from raw materials, which had been the other primary educational context that the hobby had provided alongside the engine tuning, and replaced it with an assembly process that was faster, required less skill, and produced a result that was, in many ways, better than what an intermediate builder could achieve from scratch. The electric motor revolution that began in the mid-2000s changed the physics of the hobby's most fundamental experience. The brushless electric motor and the lithium polymer battery together produced aircraft that were quieter, cleaner, and simpler to operate than glow-powered aircraft. No fuel to mix, no glow plug to replace, no needle valve to adjust. The electric motor started instantly and reliably and produced consistent power through the flight without the management that the glow engine required. These were genuine improvements in the experience of operating an RC aircraft, and they attracted genuine converts. And what they removed was the specific friction of the glow engine and the specific knowledge that friction delivered. The pilot who learned on a glow engine understood something about internal combustion that the pilot who learned on electric did not understand. That they understood about the relationship between fuel mixture and power output, about the operational consequence of a lean run versus a rich one, about the specific discipline of engine management that the glow aircraft demanded before and during every flight. This was not trivial knowledge. It connected the model pilot to a broader understanding of how combustion engines worked, an understanding that had practical applications in every other context where combustion engines appeared. What happens when mechanical tuning disappears? The question is not about nostalgia. It is about capability. The specific capability that develops through the practice of tuning a physical system that has real requirements and communicates them directly and honestly. The glow engine did not forgive inattention. The needle valve that was set too lean would destroy the glow plug, and subsequently the engine if the lean run was sustained. The fuel tank that was improperly plumbed would feed air into the carburetor at certain flight attitudes and cause the engine to quit at the moment when quitting was most consequential. The glow plug that was wrong for the fuel mix would not maintain the correct head temperature, and the combustion would be inconsistent, and the engine's power output would be inconsistent, and the aircraft's behavior in the air would be inconsistent in ways that could be difficult to diagnose if you had not already developed the knowledge of what consistency looked like when it was correct. All of these potential failures were manageable. They were manageable because they were predictable, because the engine communicated its condition through sound and smell and feel, in ways that could be interpreted by someone who had paid attention over time. The modeler, who had tuned a Veco through 100 flying sessions, had developed a comprehensive model of how the engine behaved under various conditions, and this model allowed them to diagnose and correct problems before those problems became failures. This is mechanical intuition, and it is a specific kind of knowledge that develops through sustained engagement with mechanical systems that have real consequences. What we lose when mechanical friction disappears, when the engine that does not require tuning replaces the engine that must be tuned, is not the inconvenience of the tuning process. The inconvenience was real. And its elimination is a genuine improvement in the experience of flying RC aircraft. And what we lose is the knowledge that the tuning process delivered, the specific, felt, embodied understanding of how a small combustion engine works, what it needs to run correctly, and how it communicates its condition to the person responsible for it. This knowledge does not exist at the level of general principles. It exists at the level of this specific engine, this specific fuel mix, this specific altitude and temperature and humidity, this specific propeller load. And it is knowledge about the particular rather than the universal. And it is the knowledge that lives in the hands rather than in the head, that is available instantly in the context where it is needed rather than after deliberate consultation of remembered rules. It is the kind of knowledge that the Veco engine delivered to the people who spent time with it through the specific education of failing and succeeding in the process of making it run correctly. If you tuned a glow engine, if you have a memory of a Veco or finally running cleanly after 3 sessions of needle valve adjustments and fuel line debugging and glow plug changes, leave that memory in the comments. The community that built this knowledge, that transmitted it through the informal apprenticeship of the flying field, is still alive in the people who remember it. The record of what mechanical engagement with glow engines actually gave to the people who practiced it is worth keeping, and the only form it can be kept in is the specific, felt account of someone who was there. Return to the circle. The model is at the end of the lines. The circle is 40 feet in diameter, and the model is making the specific sound that a correctly running Veco makes at full throttle. The clean, 2-stroke note of an engine that has been prepared correctly and is delivering what it was designed to deliver. The lines run from the handle in your hands to the bell crank in the model's fuselage. And through the lines, you can feel faintly but specifically what the model is doing in the air. The needle valve is at the setting you found on the 3rd flip of the afternoon, after the first 2 attempts told you the mixture was too rich and you corrected by a 1/4 turn, and then a slight adjustment back. And now the engine has been running for 2 minutes, and the sound has not changed, and the exhaust is the color and consistency it should be. And the model is in the inside of its circle, making the specific sound of something that has been made to run and is running. Veco Products made this possible. And not just the engine, the entire ecosystem of components and the accumulated engineering judgment that went into each one, the tanks and the horns and the wheels and the fuel delivery system, all of it organized around the specific requirement of an engine that demanded correct preparation and rewarded it with performance that the unprepared engine could not produce. The company closed. The name disappeared from the engine boxes, though the designs lived on in the K&B catalog for decades. The hobby shop where the Veco was purchased is gone, or has become something else. And the cracked asphalt where the circle was drawn is probably a parking lot, or a subdivision, or a park, where model flying is not permitted. But the knowledge is not gone entirely. It lives in the hands of the people who tuned these engines, who carried the feel of the correct needle valve setting in their fingertips through every subsequent session, who can still hear the difference between a rich run and a lean run in the memory of what the circle sounded like on the best of those afternoons. The engine is still running. The circle is still there, in the memory of everyone who ever stood at its center.